Hi fellow enthusiasts, welcome to my channel. Let's go into today's video and we're gonna come back at the end to wrap it up. In this episode, we'll be showing you how we built this TV transmitter. Well, we will not be starting from the scratch, but we'll give you some theories, some backgrounds on how to build a TV transmitter. And once we show that, then we're going to go back and do some other extended tutorials, how to make the components that we use vis-a-vis the inductor that we used, and then how you come up with the channels that you're going to build your transmitter to target. So you would have seen this video. If you haven't seen it, please go and watch it. So this is the TV transmitter, color TV transmitter. We have a simple camera here, a simple camcorder, and then we have an analog television set. And then of course we have small electronic component that we used to transmit the signal from the camera live to the TV. All right. So let's start by laying some ground rules. First of all, the TV transmitter you're seeing is, or every TV transmitter you know has two components that is transmitting. It's transmitting an analog component, an audio component and a video component. So for each channel, this is the US TV channel. So if you're in the US and you have an older TV set in your home lying around somewhere in your basement, like mine was in my basement, still in my basement, if you want to use it or just want to learn how things work, because here in this channel we'll teach you how things work, we show how things work. As for each channel, there's a channel bandwidth or band limits. The band limits simply tells you the lower side of the band and the upper side of the band. So between the lower and the upper is about 6 megahertz. Some use 5.5 megahertz, but as you can see here, 54 to 60 is 6 megahertz. That's for channel 2. In channel 3, from 60 to 66, channel 4 from 66 to 72, and so on and so forth. So you can see easily when you build a TV transmitter, it has to have a very huge bandwidth, 6 megahertz bandwidth. Now, each of them, you have a pilot for that bandwidth, and then you have the analog video being transmitted on this frequency, and then the analog audio on that frequency. So basically you need two transmitters, and those two transmitters, the analog will be the audio will be transmitting at 59.775, and then the video will be transmitting at 55.25 megahertz. And then remember the limit is 60, so you have about 0.25 at the end. Let me just draw something up. Let me just bring this up. Okay. And we're going to try to represent the bandwidth. So say we have for channel 2, we have 54 as the lower limit, and then the upper limit is at 60. And this is megahertz. We are saying you can transmit anywhere here, but not really from 54 and not really up to 60. So you're going to leave a gap here of about 0.25 megahertz. The reason for that is the next channel starts right after this, and that one also leaves another gap, a little bit of gap here, and wherever it ends, it also leaves another gap for the next channel, so there's no crosstalk. And if you go back to this, you can see the next channel starts at 60, which is the same place that the first channel ended. Starts at 60, but your audio doesn't start until the video doesn't start until 61.25 and ends at 65.75, so leaving 0.25 at the end. And also the audio doesn't start until 61, and the pilot doesn't start until 60.31. So at the beginning you have 0.31 gap. So right here, you're gonna have a gap of about 0.31 megahertz. This ensures there's no interference with the channel before. Likewise here, 0.31 megahertz. Then you have your pilots going right here, and then you have your audio video signal transmitted within here, and then there's a gap, and then your audio signal is transmitting here, is transmitted here. So this will be your video, this will be audio. All right, within this bandwidth. So we're going to show you how this is done. So you need a mixer. So really, to build a good TV transmitter, you need the video source or video input. It could be from a camera like we did, or from a recorded video, and then you're gonna have maybe an attenuator. In our case, we use the variable resistor to just control the amount of signal going into the mixer. So you have a mixer here, and then you have an antenna. We always draw an antenna that way, but then you need the audio signal. Now your audio signal, let's make this a little bit smaller so we can see everything together. Now your audio signal has to go through, let's say we have an oscillator here, 5.5 megahertz oscillator, or in this case we're using 6 megahertz oscillator, and then this oscillator is modulated by an audio signal. So audio in, and this will be video in. So you can vary the signal here. In some cases, you might want to have a capacitor here. Again, we always use capacitors at the input to isolate the DC conditions. So you can do the same here. Isolate DC conditions of the sources. So just use capacitors. So this is really what it is. So you can have this would be a mixer, and then your audio in, video in, and then your antenna is right there. So antenna. The key thing we want to show you here is, for every channel you need your video transmitter and you need your audio transmitter. And we have demonstrated that you can use a simple FM microphone, wireless microphone, as a TV transmitter. But the way we've built our FM transmitters, you can go to my channel and just pick any transmitter we have on the channel. Pick any transmitter from HackerNet or even HackerWorld. So let's try that. Pick any transmitter there, and we can make it a TV transmitter. So let's go and let's go to FM transmitter. Alright, so we have so many FM transmitters.
To boost your team's efficiency.
But let's just go to this channel and see the transmitters. We have walkie-talkie, all videos. Now I needed to go to transmitter. Let's go to playlist.
Hi fellow enthusiasts, welcome to my channel. Let's go into today's video, and we're gonna come back at the end to wrap it up.
Alright, AM transmitter, walkie-talkie, TV transmitter. What do we have in TV transmitter? How many? Oh, we just have one.
Hi fellow enthusiasts, welcome to my channel.
Receiver.
Let's go into today's video, and we're gonna come back at the end to wrap it up.
Alright, so let's pick microcontroller now. 8020 transceiver modules, FM receivers.
Right, there's a camera right
This is
there.
a one transistor FM transmitter.
I'll send it to you. Little pixelation or raster.
Let's try this one here.
What shall I render to Jehovah? For he has done so very much for me.
Alright, so this is a walkie-talkie, but the circuit diagram here could serve as well. Because we use FM transmitters to make our walkie-talkie.
The way around.
So you can pick any transmitter you like this one here. You can take this transmitter, or you can take any of our transmitters, to be frank. I'm just gonna try to find a one transistor. Picker word, one transistor, FM transmitter. Do we have that? Yeah, this one here, or that one, or that one. Yeah, we have a lot of one transistor transmitters, lots of them. All right, so let's which one do we pick now? There's so many now, so let's just take this one here. All right, so you can take this transmitter and just pause it around 109, and this will be your good TV transmitter. It is an FM transmitter, right? But I will show you how to modulate this transmitter. Remember, I have another circuit diagram here I was going to show you, but I just want to show you how you can take any TV transmitter, any FM transmitter we have built, and make it a TV transmitter. So let's say we use this USB transmitter, Heckerwood one transistor, Heckerwood USB one transistor FM transmitter. You can take this transmitter and turn it into a TV transmitter. What you need to do is to modulate this transistor transmitter. You need to modulate the amplitude if you want to send video. So let's go back and into this theory. Remember, this channel is the long one where we talk a lot and we just talk about the theories. So there are two types of modulations that we're going to talk about here. There's the amplitude modulation, there's the frequency modulation. In amplitude modulation, you modulate the amplitude. And in frequency modulation, you modulate the frequency. You get that? Now, so basically, if I have a signal from my oscillator that goes like this, let's say, if the amplitude should be the same, so I gotta redraw this because let's just give it right. So let's say the amplitude is here. So if I have my frequency going this way, my waveform going that way, and if I do anything to this waveform such that the amplitude doesn't always go the same, let's say for any reason it goes if it's different from the steady state, then I've succeeded in modulating the amplitude. Normally what you do is you add an audio signal that creates a duplicate waveform, so it kind of envelopes your amplitude that way in a duplicate form. Don't mind my drawing. Okay, I think I can draw better. Let's try again. Okay, better. And then the waveforms will just be within this envelope. And don't mind that they're not uniform, but they should be uniform above and below the center line. Should be uniform. So this will be your amplitude modulation. So this component, the oscillator signal, will be high frequency. And when I say high frequency, compared with your audio signal, which is creating the envelope. So that modulates your amplitude. So your amplitude doesn't stay the same. Let's just use this line. So this was your original amplitude, but your audio signal has forced it and created an envelope and compressed the amplitude and reduced the amplitude of your signal. Now this carrier, this high frequency component will be what we call the carrier. That's what takes your signal out and through the airwaves to your receiver. Remember, we mentioned that if you can get an oscillator to oscillate around 100 kilohertz and above, you should be able to transmit that signal, following the skin effect theory. But this is what happens with amplitude modulation. Now, the other modulation we talked about here is the frequency modulation. In frequency modulation, just assume the same frequency we had. Let me just keep the amplitude. So the amplitude in frequency modulation remains the same, but your audio signal creates. So if let's assume this is your frequency. Again, ignore my drawing, but just assume there's the same spacing. Assume this is the same spacing. Okay. So if this is my carrier signal, so the one that takes my information signal and transmits it out. So this will be my amplitude, and that would be my frequency that way. Now, if I add my audio signal, which is a lower frequency signal, again, it might look anything like let's do this. Might look anything like I'm saying something. So normally your signal will go like, when if you have a recording device and you look at the audio signal, it just looks somehow something like this. So let's just pretend that this is the amplitude then of my audio signal. Now, when you take this and you superimpose it on the carrier signal, you get something not quite like the original. So it will be like the modulated signal, the amplitude, the frequency modulated signal will still keep the same amplitude, but the frequency will change. So you will see something like um, I'll intentionally space it out so you can understand what I'm doing, and then it will compress sometimes, and then it will space out sometimes, and so on and so forth. The key here is that the amplitude remains the same. This is the reference, which is 0. The amplitude remains the same, but the frequency changes. So you use the frequency modulation to transmit your audio signal, and then you use your amplitude modulation to transmit your video signal. This is what we're gonna do. Now I'll show you an easy way to modulate any transistor-based transmitter to become an amplitude modulated transmitter. All right, so we won't have time to discuss transistor biasing in details, but let me just do a little bit of that. So if I think I've talked about this for quite a while, that I need to actually um, maybe make a tutorial on this. But I'm just gonna draw this quickly. We can talk about it. Okay, so if this is my load, this is my RC, this is R1, R2. I can just have my input signal here, and I need a capacitor here, so input signal, and then this is my RE, and then this is my transistor Q1. Now, this is my base, not if. This is my base, and this is my collector, this is my emitter. Now, the voltage from the base to the emitter, which is the VBE, for a silicon transistor 0.6 something, let's just say average of 0.7 volts. And for this transistor, my gain is a component of my RE. So the gain is based on the value of my RE. So whatever value I have here, without discussing the biasing, because I see myself being drawn into explaining everything, how to center the outputs, with respect to your quiescent current and the rest of them. So let's not go into that now because we're going to be drawn away from it. But I just want you to know that the gain varies with the RE. That's all we just need to know now. And this gain is all about the amplitude. The gain varies RE amplitude. Now, if I do anything to be able to change the value of this, remember you normally choose the value of RE for temperature stability, such that the value, let's say if you keep the value of VBE plus, so this will be your VE. If your VE is approximately, let's not say approximately, but let's say is greater than or equal to 1 volt, then you're ensuring stability when the transistor heats up. But at the same time, the value of RE, remember that you have a collector current flowing down, right? And that will also interact with the IB. So small IB will cause an increase in IC or IE, and IC is equivalent to IE. Again, I think we must do a video on this. We must do a video on this. But let's just pretend now that IE is IC. So if I do anything to change the value of RE slightly, ever so slightly, if I make it a little bit less, then I can increase my gain. Or if I make it a little bit more, then I can decrease my gain, or and so on and so forth. So if I can do something to this RE, what will it be to change the value, but also to keep it at this during my biasing conditions? I want that at my biasing conditions, I have my VVE to be greater than or equal to 1 volt, but under operating conditions, I want the value to change slightly. What I can do is to find another resistor and put in parallel with that. But if I put any resistor in parallel with that, then the effective resistance will be less than the lesser of the two. So if I have two resistors in parallel, so let's just delete all this here and just put another resistor in parallel here. If this is RE and this is RE prime, then RE effective will be definitely less than the lesser of the two, whichever is less of RE or RE prime. So will be less than the lesser of the two, will be lesser of RE in RE prime. That's the effective resistance. But then if it's such a critical value that my that it puts my my temperature stability, we're shooting for 1 volt, if that puts this at a risk that we can have less than this, less than 1 volt, then this transistor will not be stable. So what I want to do is, instead of connecting a resistor in parallel, it doesn't matter the value I connect in parallel. As long as I have two resistors in parallel, the effective value is less than the least of the resistors in parallel. Like conversely, when I have resistors in series, the least value of the resistors in series is greater than the biggest value of the resistor in that series. I think we talked about this in our resistor configurations. I'm just going to draw it quickly. So if I have R1 and R2 in series, no matter what I do, the least value of this combination will be greater than the least of the two. Likewise, when they're in parallel, the least value in the combination, the greatest value in the combination is less than the least of the two. All right, so let's just delete this. You can watch our video on resistor analysis and stuff like that. I think it's in our basic electronics. Now, all I wanted to show you here is that if I instead of connecting a resistor in parallel, I can connect a resistor in series with a capacitor, And this resistor is only called into action when when it is operating, not during biasing conditions, but when it's operational, because the capacitor will block DC conditions, so it will take this out of the equation. Only during my operating conditions, during AC conditions, does this path come into effect. And when that comes into effect, I can actually influence the gain of this transistor slightly. And so that's how you're going to create amplitude modulation, right? So because the emitter resistor is what controls your gain. So what I want to do is I want to have a condition here where I have a value that goes into I have a signal that goes into the emitter circuit, and that signal is modulating what is happening in my emitter circuit and causing the gain to change according to the signal that is coming into it. So with that, I can create an amplitude modulation. And then if that's my video signal, then I can transmit that video signal and receive it on a TV that corresponds with um, the oscillator. So in this case, I won't have a resistor here. I will have a tank circuit. And I'm going to show you how to calculate that. So I'm going to have a tank circuit, which is an inductor and a capacitor in parallel. So I'll use a variable capacitor so I can tune that. So with this system you have right here, you can choose any value you want for R1 and R2 to center the VCC. And whatever the value you get at VCC, add 0.7 to it. Right, whatever you get at the this point here, let's just call this VB. So whatever you get for VB, if you subtract 0.7 from it, that will give you VE, because VB is VBE plus VE. Um, so what I mean by that is the voltage across R2 is the same as, where is my tiny marker? So voltage across R2 is the same as voltage across RE plus voltage across base and emitter. Basically that. So this voltage that you measure from this point, I'm going to use a red marker. Voltage I'm measuring at this point is the same as whatever I have in my VE, voltage across the emitter resistor, plus this voltage drop between base and emitter. Okay, so that's, choose any value for R1 and R2 to put this point at the center of your um, VCC, and then whatever your value of VCC is, just make sure that if you're keeping this RE at 1 volt, greater than or equal to 1 volt for temperature stability, I would choose my VBE to be at least 1.1 at least. Then you're going to add 0.7 to that, and then you're going to get approximately 1.8 volts. So choose a value that puts your VB to be at least, so this is VBE is this one, and then sorry, this is VE. VE is that portion, then VBE is this portion, and then this one is your VR2 or VB. So choose a value or two values of resistors that puts this point at least 1.8 volts, right? And then of course, when you're choosing that, make sure that the current being drawn from the collector, which is collector current is equivalent to emitter current, that will give you that value of current multiplied by value of a resistor will give you 1.1 volts, which is this guy here, right? So again, we're going to do this theory later. But now, so choose any value, any two values of resistors that puts your VB at that point, and then choose the appropriate value of V of RE to give you VE of 1.1 volts or greater, and then you're good to go. Then just connect your audio signal here. And but like I said, you can use a resistor and capacitor in series to create to make sure that this resistor doesn't shut out your the base, um, the emitter resistor, which um, which if you have the two in parallel, you will have a base resistor that is less than the least of the two in parallel. To avoid all this, because I think I've given you a lengthy path, one other thing you can do is, I'm not going to draw the rest of the circuit, I'm just going to draw the resistor alone. One thing you can do is, instead of having a fixed value resistor, you can use a variable resistor here. And then you have a capacitor here, and you have your video in here. I always like to have a capacitor here because capacitors are DC block and AC. They are DC open and DC short. AC open, DC short. So as far as AC conditions of biasing this transistor is concerned, this is an open circuit. It doesn't mix the biasing conditions with the video signal, and then the DC conditions of your video source doesn't mix with the DC conditions of your transmitter. So I put this capacitor here. You can use a very small value, 0.1 or less. And then as you vary this resistor, you are increasing or decreasing the modulation. You're either saturating, oversaturating, or undersaturating the the video signal to the transmitter. So build this. When you do this, you are changing the amplitude of the signal, and when you change the amplitude, that is called amplitude modulation. And you are changing the amplitude based on the video signal. When you do that, you create amplitude modulation, and then amplitude modulation is what transmits to your TV. And then you can also do the converse by modulating the bass. When you modulate the bass, you're modulating the frequency, and that will create your frequency modulation. But we're not going to talk about all that in one video. We're going to do another video where we show you the full maybe the full picture. But just look at this mixer that we've built here. We've shown here the block diagram. So there's a mixer here. You have an oscillator, audio frequency not audio frequency, but sorry, it's kind of 5.5 megahertz oscillator, and that you're going to mix your audio signal, and then use that to increase the bandwidth of your video signal, and overall you will have, at your antenna level, you have a very big bandwidth. So 5.5 megahertz, and then within this will be your video first, and then your audio signal. Okay, now we've done a lot of theory, so let's just go to the circuit that we've drawn for you, and we'll show you what we've been talking about. So right here, again, you can see I didn't put that capacitor, so let's add it. We didn't add that capacitor, so let's duplicate one of these capacitors. We're just gonna connect it here, and let's make it 0.1. All right, so we're gonna call that one 0.1. All right, so the video in, we have the variable resistor to modulate that, and that is it right there, and your transmitter is good to go. Now this value here, I think in actual sense, I think we probably use 4.3 kilo. I think we use 4.3 kilo, so 4K2 4K3, sorry, I think we use 4K3 in the actual implementation. So 4K3 is what we used. And so build this. You have in the next one, it's going to be live stream as well. In that one, I haven't checked if anyone has posted any question, but in the next episode, we're going to show you how we're able to calculate the values for each of the channels you're building this for. Again, this is for educational purposes, just to show you how things work. I'll go back to that TV channels. So if you wanna, I built mine for channel 2. So you're gonna get the analog signal, the analog video at this frequency, and then your analog audio at that frequency. Again, you can build two separate transmitters, and you power them up together. I just have one amplitude modulated and one frequency modulated. The frequency modulated will be your audio, and the amplitude modulated will be your video. And then once you tune your TV to channel 2, it is capable of receiving this duplex transmission, right? But you can use one transmitter to achieve that by building it in this way. So we're going to show you how to um, build that subsequently, not in the next episode. In the next episode, we're just going to concentrate on talking about the audio transmission, and then maybe showing you, all right, so maybe we'll show you how to calculate the frequencies from a chart. We'll show you a chart or maybe a website how to calculate the frequency given the inductance and capacitance. Or you can just I'll show you the website, and then in the next video, this website Omni Calculator, in the next series we're going to talk about that. So we're going to come from here, pick a frequency of choice, or we'll say we want to calculate for frequency. Pick one of the components, the inductance, and calculate the capacitance, or pick the capacitance and calculate the inductance. Or we can show you actually how to make the inductor, so you can make an inductor for whatever frequency you want. So you can do it bottom up. You can start from where you want to end, which is I want to build a transmitter for channel 13, let's say, for channel 13. So you ask yourself, what will be my video frequency for channel 13? You're going to build your oscillator for this, for your video signal, and then for your analog signal, you're going to build your oscillator for this. We also show you how to use a frequency meter to measure the oscillator frequency and all that. So again, this is the longer version of the video. We showed you the shorter version, which is the 2 minute version. I think we still have it here. The 2 minutes version, 219. Yeah, 2 minutes version of how to make a TV transmitter, and then we're showing you the extended version how this is designed from ground up. All right. So we picked a channel. I'm gonna talk through it one more in a way of summary. So pick the channel. We say we want to build a transmitter for, let's say, channel 20. Let's say channel 20. When you start from there, you're gonna know your video signal. This is your bandwidth. Bandwidth is still 6. So you start from 500, ends with 506. Your pilot is at 0.31. So after 0.31, you're gonna have your video here, and then your audio at that point. So the difference between the video and audio is about 4.5 megahertz. So you're transmitting your audio 4.5 megahertz above your video signal. Pick any other channel, it is similar. So we're picking channel 20 just as an example. I think I'm looking at 19 now. Channel 20 as an example, you're gonna build a video transmitter at 507.25 and your audio at 511.75. That's what you do. So pick any one you like and then build a transmitter, two transmitters, or you can build one transmitter and have an increased bandwidth. And that's what we're showing here. You can have one transmitter, and then just your audio will be coming in through a 5.5 megahertz transmitter. So you can build two transmitters and you just mix them up. So have one 5.5 going into one let's say 200 megahertz, and then the output here will then be about from 200, so it's going to be 205.5, the frequency. So the bandwidth will really increase. And then this one here contains your audio. So your audio will be at the top end of this spectrum of this 200 to 205. And then your video will be somewhere earlier. We're gonna build all that and show that, but it will be in maybe several weeks from now, um, because we have other videos that I want to show you. Let's start from next video to show you how to calculate this. We've shown it in other videos. If you want to go look at that, go ahead and look at that. And then sometime later, we're going to show you how to bias a transistor. Okay, I have to recap now why I'm showing you this. Many times, as enthusiasts, what we do is we see a video someone has built, and we are impressed, so we're inspired, and then we go ahead and replicate it. And many times I see people on my channel saying, what is the value of that resistor? What is the value of that inductor? What is the value of that capacitor? Sometimes I miss labeling things. Sometimes I don't give the values. I don't give the labels. I just draw it, and I built it, and it's working. Like here, I had 8.2 kilo ohms resistor because I probably had copied it from one of my circuits here and just like duplicated the circuit and just made modification. Or when I copied the value, when I took the value from the library, I just maybe kept it that way. And sometimes I want to edit it, but I made a mistake and put a different value. And what happens then is someone asks me for that value. Why do you have that value there? For instance, this is a good example here. We have C5. And C5 here, asterisk C5. All right, you see now I have C5 here and then another C5 here. So this should be C5. This should be C6. This is one good example. But let's say C5 when I have asterisk C5. And then I said in the note here, choose C to match the antenna impedance for chosen frequency. Now, you want your antenna impedance to be 50 ohms or 70 ohms. Let's say 50 ohms. You want your antenna impedance to be 50 ohms. And you know how to get the impedance. Capacitive impedance is XC, or capacitive reactance. XC is 1 over 2 pi FC. 1 over 2 pi FC. So you're going to choose the frequency of choice that you're building this for. Again, we say we're doing this bottom up. So you start from the bottom. You say, I want to build it for channel 2, like in my case. I want to build it for channel 2. And then this is your channel bandwidth. So you take this frequency and say, what value of C would I choose? What value of C would I choose to give me about 50 ohms? And then you can calculate it backwards because you know your frequency, you know your resistance. Pi is a standard 22/7. The only thing you don't know is your C. You calculate that and get the value of C. You can do that for 54 megahertz, and then you do the same for 60 megahertz, and then you can find the middle point. If you want to optimize for your audio signal or you want to optimize for your video signal, you can choose the value that closely align with what you want to optimize for. And then that is the value of your C to match your impedance, which is the interface impedance, about 50 ohms. So that's what you do. And now, if I had put a value here of 27 ohms, and someone comes to me and say, why did you choose 27 ohms? Or maybe they say, I built the same thing, I use 27 ohms, but I want to build it for channel um, 50 or channel, let's pick a higher number of channel. Let's say, okay, yeah, let's say 50, why not? Which is about 680 something megahertz. And it doesn't work well for me. Well, it wouldn't work well for me because you are going for 600 plus megahertz. I'm going for 60 megahertz. At least there's a factor of 10. So the value will not be the same. So while my uh, antenna could be offering a 50 ohms impedance, for you it could be offering 5 ohms or 500 ohms impedance. In fact, because it's an inverse relationship, it's going to be offering 5 ohms impedance, right? So in that case, it will not match. It will not work as efficient as mine. And that is why in these videos, I show you why things are done the way they are done, so you don't just copy and repeat. Again, these channel lists are for US. I think there are other ones for Europe and other places. And some parts of the world use American standard of TVs and stuff like that. So if it is the same case, then there's no problem. But the theory is the same. You pick any value that your TV supports, pick any value. And again, it is important that you know the region your TV is made for, because that will tell you what the frequency corresponds to. Not all the channel 2s correspond to 50 to 50, 54 to 60. So find out in your region of the world what kind of TV you're using. Then when you find that out, you go on the internet. This is from Wikipedia. So go on the internet, find the frequency that corresponds to your TV station. Again, this is for analog. Now find the frequency that corresponds with that, and then in the next episode we'll show you how to use all these calculators, this online calculator, to find the frequency and the components you need to make for uh, your inductor, and then to choose the value of capacitor, and then you're going to find the value of your asterisk C5, find the value to build your transmitter. Then after that, we'll show you how to build a combined system with the audio and also the video in one. But remember, this oscillator is voltage controlled oscillator, which means as the voltage drops, the frequency changes. This is not ideal. This is not the best that we can do. So you can use in the next video we'll show you the circuit diagram, how to add regulators and other alternatives that you can use to help you build a more stable transmitter. All right, so this is where we're going to end it today. If you have any question, let us know. Otherwise, I must see you in the next one. All right. Thanks for sticking around to the end. That'll be it from us today. Please, if you have not subscribed, do so right now. And don't forget to like and share this video. Until we come your way again with more contents, stay enthused.